Welcome to techdaily.ai. Today, we're diving deep into something, well, something most of us use literally every day, probably without even thinking about it. Bluetooth. I mean, think about it, right? You tap play on your phone, and somehow, just wirelessly, all those ones and zeros, millions of them just show up at your headphones. Your music just starts. It honestly feels a bit like magic sometimes. But how does that really work? How do those bits actually travel through the air, like every single second? So our mission today is to really pull back the curtain on the pretty ingenious engineering behind Bluetooth and explore the basic ideas of wireless communication that make it all tick. Before we jump right in, just want to mention that this deep dive is sponsored by Stonefly. They're your trusted solution provider and advisor for enterprise storage, backup disaster recovery, hyper-converged VMware, Hyper-V, Proxmox clusters, AI servers, SA365, that's a turnkey security appliance, and public and private cloud solutions. You can check out stonefly.com for more info on all that. Okay, let's unpack this thing. So to really get our heads around this invisible conversation happening,
Where do we start? Like, what's a good way to picture signals moving without wires?
That's a great place to start. Maybe think about traffic lights.
Traffic lights.
Okay. Yeah, you instantly know what they mean, right? Because they use different colors, which are really just different wavelengths of light we can see. Green light waves are around 540 nanometers, red around 700. Our eyes see the difference. Our brain gets the message, go or stop.
Right. Gotcha. Different wavelengths, different messages.
Exactly. Now, your phone and earbuds, they do something similar, but they use a different part of the electromagnetic spectrum, one that's invisible to us. Specifically for Bluetooth, the waves are much longer, around 123 millimeters. And unlike visible light, these can actually pass through things, like walls, which is why your phone can be in your pocket and still connect.
Ah, okay. So 123 millimeters,
Yeah.
invisible waves. How does that send ones and zeros then?
Well, your smartphone basically assigns slightly different wavelengths for a 1 and a 0. Maybe, say, 121 millimeters is a 1 and 124 millimeters is a 0, just as an example. But here's the really amazing part. The antenna in your phone switches between those two wavelengths incredibly fast. We're talking about roughly 1 million times every second.
1 million times.
Yeah. And that rapid switching, that's how it sends millions of those ones and zeros every single second. It's pretty remarkable.
It really is. And I guess visualizing that is tough. We always see those simple wavy line diagrams, the
Right.
sine waves.
Right. And those can be a bit confusing, honestly, because electromagnetic waves don't just travel in a neat line. They spread out from the antenna, more like an expanding sphere.
Like ripples in a pond, but in 3D.
Kind of, yeah. So those sine wave diagrams, they're useful maybe for showing frequency or wavelength, but they're just like a tiny slice of that expanding sphere.
So what other ways can we picture it?
Well, you might see diagrams showing like binary numbers traveling. That shows the data, but not the sphere part or the frequency changing.
Okay.
Or you could have diagrams of expanding spheres, which show how it radiates out, but it's hard to show the frequency or the actual data on those. Sometimes you see simplified spheres, maybe just to show devices talking on the same frequencies. The point is, different pictures help understand different parts. No single one captures everything perfectly.
Makes sense. You piece it together.
Exactly. And speaking of frequencies, Bluetooth operates in a very specific little slice of the radio spectrum. It's usually called the 2.4 gigahertz band, which corresponds to wavelengths between about 120.7 and 124.9 millimeters.
2.4 gigahertz.
Yeah.
That sounds familiar. Isn't that where Wi-Fi lives too?
It is, yeah. We'll get back to that. But within that Bluetooth range, imagine you're in a busy place, like a coffee shop. Loads people using Bluetooth headphones, keyboards, mice.
Right, a potential mess.
It could be. So to manage that, the Bluetooth standard divides that frequency range into 79 distinct channels.
79, okay.
Yep, each channel uses its own specific, slightly different wavelengths for its ones and newers.
But wait, if there are 79 channels and lots of devices, how do my earbuds know to only listen to my phone? How does that exclusivity work?
Ah, that is the crucial question. And the answer lies in how the messages are packaged up.
Packaged, like sending a letter.
Exactly like that, yeah. The data isn't just a continuous stream. It's broken down and put into these little digital envelopes called packets.
Okay, packets. What's in them? Well, the first part is really important. It's called the access code. It's a 72-bit unique identifier. Think of it like a very specific address on that digital envelope. So only my earbuds, which know my phone's access code, will even look at that packet.
Precisely. It synchronizes the specific devices. Then comes the header, That's 54 bits. It's like the information on the outside of a package tells the earbuds what kind of data is inside, how much data there is, things like that.
Got it. Address, description.
And then finally, you have the payload. That's the actual stuff you care about, the music data, maybe voice from your microphone. And the size of this payload can vary quite a bit, from maybe around 100 bits up to over 8,000 bits, depending on what's being sent.
Okay, so access code, header, payload. That makes sense for getting the right message to the right place. But what about all those other devices using the same 79 channels? Doesn't it still get crowded?
This is where it gets really, really clever. It's a technique called frequency hopping spread spectrum, or FHSS.
Frequency hopping. Sounds like it jumps around.
It does. Your phone and earbuds don't just pick one of those 79 channels and stick to it. Instead, they jump between all the available channels.
All 79. How often?
Get this. 1,600 times every single second.
Whoa. 1,600 times a second. That's insane.
It's incredibly fast. After each tiny hop to a new channel, they send just one packet, that access code, header, and payload.
And how do they know where to jump?
Your smartphone dictates the sequence, like it's calling out the dance steps, and your earbuds follow that exact same pseudo-random sequence perfectly in sync.
Wow. And what if a channel they jump to is, noisy or something?
That's the beauty of it. If a channel is congested, maybe because of interference from Wi-Fi or another Bluetooth device, the smartphone just tells the earbuds, okay, let's skip that one for now. They just omit it from the hopping sequence until it clears up.
So it's constantly adapting to the environment.
Exactly. It makes the connection really robust.
Yeah.
And there's another huge benefit: security.
How so?
Well, because the hopping sequence is unique to your paired devices and changes constantly, it's incredibly difficult for someone else to listen in. They'd have to know the exact sequence out of billions of possibilities, changing 1,600 times a second.
Right. That makes sense. Hard to eavesdrop on a conversation jumping that fast.
Yeah. And one more thing about robustness: if for some reason a packet does get missed or corrupted during transmission, maybe due to a burst of interference.
What happens? Does the music stutter?
Usually not. The earbuds basically send a quick message back saying, hey, I missed packet number 1234, and the smartphone just sends it again on the next hop. It ensures the data gets through accurately.
That's incredibly sophisticated for something we just take for granted.
It really is. And fun fact, that frequency hopping idea wasn't invented for headphones. It actually dates back to World War II, developed for secure military communications.
No way. So it's like military-grade tech in our pockets.
In a way, yeah. Miniaturized and adapted, of course, but the core principle is there.
That's fascinating. Okay, so frequency hopping helps deal with crowding and adds security.
Yeah.
But you mentioned earlier that the 2.4 gigahertz band is shared, with Wi-Fi.
And other things, too. Some industrial equipment, scientific instruments, medical devices, and probably the most common one you might notice at home: your microwave oven.
My microwave. Really?
Yep. Microwave ovens typically operate right around 2.45 gigahertz, smack in the middle of that band. So if your microwave is running, especially if it's an older one, maybe leaking a bit of radiation,
It could interfere with my Bluetooth signal.
it absolutely can. You might notice dropouts or stutters in your audio if you're standing near an operating microwave.
Oh, good to know. And you said leaking radiation. Is that dangerous?
Good point to clarify. The power levels are very different. Think about the light from huge stadium floodlights versus the light from your phone screen. Both are light, but the intensity and potential effect are vastly different. Microwave ovens are designed to keep the energy inside. The levels Bluetooth uses are extremely low power.
Okay, phew.
Huh.
But it's still enough to cause interference sometimes.
Yes. And here's a quick safety warning. Definitely do not put your phone or earbuds inside a microwave and turn it on, ever. It will destroy them.
Right. Good PSA. Don't microwave your gadgets.
You can do a little experiment safely. Put your phone inside a microwave oven turned off, completely off, and close the door. The metal box acts as a shield, a Faraday cage. You'll likely see your Bluetooth connection to your headphones drop immediately. It shows how effectively that metal mesh can block the radio signals.
Interesting. A little home experiment. So we have microwaves, other Bluetooth devices, and Wi-Fi also uses 2.4 gigahertz, right?
Correct. Most Wi-Fi routers operate in this band as well, though they also often use the 5 gigahertz band now too. But in the 2.4 gigahertz range, Wi-Fi typically divides the band into about 14 overlapping channels.
Oh, it's a really crowded neighborhood, electronically speaking.
It absolutely is, which brings us back to that key question.
How on earth does Bluetooth manage to send potentially megabits of audio data reliably and without errors through all that potential noise and interference?
Right. We've covered some key parts: The frequency hopping is huge, obviously. Jumping around avoids staying on a noisy channel. And the packet system, with error checking built in.
The earbuds asking for repeats if they miss something.
Exactly. But there's another layer. Inside that tiny Bluetooth chip in your phone and headphones, there's some very specialized circuitry. Its job is partly to act like a sophisticated filter.
A filter for radio waves.
Sort of, yeah. Think about how your brain works when you're driving. Your eyes see everything: signs, trees, other cars, pedestrians, the dashboard.
Wow.
It's a flood of visual data. But your brain is brilliant at filtering out most of it and focusing your attention on the important things, like that red traffic light ahead.
Okay, I see the analogy.
The Bluetooth circuitry does something similar for radio signals. It's designed by engineers to listen very specifically for the signals it expects on the frequency it expects at that exact microsecond, and to ignore or filter out all the other radio noise happening in the same band.
So it's not just the hopping, it's smart listening too.
It's smart listening, it's coordinating the hopping, checking for errors, using specific bits within the packets, requesting retransmissions, assembling the packets back into useful data, all happening incredibly fast in real time. It's a miniature marvel of engineering, really.
Okay, that paints a much clearer picture of the robustness. Let's get down to the absolute physics of it though.
Yeah?
How does waving an electric field around actually become a 1 or a 0? You mentioned different wavelengths earlier.
Right. The most fundamental method Bluetooth uses is called frequency shift keying, FSK.
Frequency shift keying.
It's pretty much what it sounds like. You key the digital signal, the ones and orders, by shifting the frequency of the radio wave. So you assign one specific frequency to represent a 1 min and a slightly different frequency to represent a 0.
Like the traffic light analogy again, but with much smaller differences in frequency.
Exactly. The circuitry generates a basic, steady radio wave called a carrier wave. Then, to send a 1 min, it nudges the frequency of that carrier wave slightly higher. To send a 0, it nudges it slightly lower.
And the receiver just detects those tiny shifts.
Detects those shifts, yeah. This method of encoding information by changing frequency is also called frequency modulation. It's actually very closely related to how FM radio works, just on a different scale and for digital data.
Huh. Interesting connection. FM radio.
Yeah. But Bluetooth isn't just limited to FSK. For sending data faster, achieving higher byte rates, it can use other, more advanced techniques too. One common one is phase shift keying, or PSK.
Phase shift keying. Okay, what's phase?
Good question. So imagine waves washing up on a beach. Frequency is how many wave crests hit per second. Amplitude is how high the waves are.
Right.
Phase relates to the timing of those crests and troughs within the wave cycle. With phase shift keying, you keep the frequency the same, but you subtly shift the wave forward or backward in time, just slightly altering when the peaks and troughs arrive relative to where they would normally be.
You're shifting the wave's rhythm, but not its speed.
That's a decent way to put it, yeah. The Bluetooth circuitry is precise enough to detect these tiny shifts in phase. Different amounts of phase shift can be assigned to represent different combinations of bits, allowing you to send more data within the same amount of time compared to just FSK.
Wow, okay. That's getting pretty deep into wave physics.
It is, but it allows for those higher data rates we expect now for things like high-quality audio.
And this communication, it's not just one way, right? My phone sends my headphones, but if I'm on a call, my voice has to go back.
Absolutely. It's fully bidirectional. Your earbuds have a microphone, and that audio data needs to get back to the phone.
So how does that work with the frequency hopping in packets? Do they use different channels?
No, they actually share the same hopping sequence. They manage the back and forth using time slots. The whole system operates in these tiny slices of time, about 625 microseconds each.
Microseconds. Incredibly small.
Very small. So in one 625 microsecond time slot, your smartphone might transmit a packet to your headphones on whatever channel the hopping sequence dictates for that moment. Then, in the very next 625 microsecond time slot, the headphones transmit a packet back to the smartphone using the next channel in the sequence.
So they just take turns really, really fast while still hopping together.
Exactly. It's like a perfectly choreographed, high-speed digital conversation, constantly switching between transmitting and receiving, all while hopping frequencies 1,600 times a second.
That is genuinely amazing.
Yeah.
The timing alone seems mind-boggling.
It really is a complex dance. And, while analogies like traffic lights or postal packets help us grasp the concepts, it's important to remember the actual physics of how antennas generate and receive these waves Well, it's a whole field called antenna theory. It's quite different from how a traffic light bulb makes light.
Right, like comparing maybe how a campfire makes heat versus how an electric radiator makes heat. Both make heat, but the process inside is totally different.
That's a great analogy, actually, yeah. The underlying principles are deep, which kind of makes you wonder, doesn't it? What other incredibly complex hidden engineering is packed into all the devices we use every day, just working silently in the background?
It absolutely does. It's just incredible. When you stop and think about it, the sheer amount of unseen engineering, the physics, the coordination, just to connect your headphones wirelessly. From, simple ideas like traffic lights to this insane frequency hopping, 1,600 times a second, assembling these intricate packets, filtering noise, shifting frequencies and phases. It really is a testament to human ingenuity. Before we wrap up, just a final word from our sponsor, Stonefly. They're offering a 100 TB immutable and air-gapped SSO NAS for just $8,995. That sounds like a seriously robust solution for anyone with significant storage needs. Check them out at stonefly.com.
It really does make you appreciate the tech more, doesn't it? Understanding even a little bit of the science underneath, it kind of demystifies it, but also makes it more impressive in a way.
Totally agree. It encourages you to think about how this digital world we live in is actually connected piece by piece.
Yeah. Well, thank you for joining us for this deep dive. Hopefully gave you a new perspective. Maybe the next time you pop in your earbuds or connect a Bluetooth speaker, you'll just take a half second to appreciate that invisible, silent symphony of millions of precise wavelength shifts happening all around you every single second. Pretty cool stuff.